Okay. All right. So thanks for joining me today. I'm really happy to be speaking. So I'm going to be talking about, sorry, just moving some things around. Some new discoveries we've made on optical emission from the inner galaxy, focusing on ionized gas in both the bar and the Fermi bubbles. So like Natalie said, I just finished up my PhD, and I'll be staying in Madison for a few months until I start in January at Space Telescope, where I'll be continuing some of this research and focusing a little bit more on how to combine UV observations into the optical work that I've been doing. Okay, so to get started, I'll just start off with one of the key discoveries, which is in the Inner Milky Way. So here's just an optical image towards galactic center. We'll zoom in a little bit closer just towards galactic center. And what you should notice is a lot of dust in the center. And just below, there is a nice bright zone. That's a region with low dust, Bada's window, where we can actually start to look a little bit deeper in. What these contours are K-band from the COBE satellite showing stellar density. And this is essentially showing you a signature of the bar in the Inner Milky Way. So a really hard to see signature. We can improve on this with better observation. So this is from the Star Horse collaboration, where they're actually able to, in a sense, directly image the bar from a face-on perspective by doing a lot of decomposition of the stellar population there. But just even in this picture, you can see a subtle signature of the bar, which is that on the left side of the image, where the bar kind of extends out closer to us, in projection that is thicker than on the right side, where the bar is extending out farther from us. So a subtle but still real effect of the bar just from looking at the star counts towards galactic center. So like I mentioned, so most of the plane of the galaxy is obscured by dust, especially for optical light. But just below, there's Bada's window, where there's a nice hole of dust. You can see it's pretty bright in this area. And this works really well to try and find optical emission from the center, where you don't have to worry about the dust as much. And what we've seen is H-alpha emission from this region of the galaxy associated with a structure that's called the tilted disk. So this is about between 1.5 to 0.5 kiloparsecs away from the center of the galaxy, and the structure that is somewhat oriented with the bar. I'll get into the details a little bit later. But the key results here are that we have more than just H-alpha light here. We have a few different emission lines. I'm showing H-alpha and nitrogen-2 here in the spectra. The stuff near 0 kilometers per second is just local emission in the solar neighborhood. But as we get to these more highly negative velocities towards minus 100 kilometers per second, this is associated with the structure, the tilted disk and galactic center. And you should be able to notice how, as you go from the local emission to the center of the galaxy, the nitrogen-2 and H-alpha somewhat invert. So you start with low nitrogen-2 to H-alpha, and in this central structure, we have really high nitrogen-2 to H-alpha, where the nitrogen-2 is actually brighter than the H-alpha. So what this lets us do ultimately, because we have even more emission lines, is kind of compare this to large samples of other galaxies using a technique called the BBT diagram, where if you look at the nitrogen-2 to H-alpha line ratio and the oxygen-3 to H-beta line ratio, all of which we're able to detect here from the structure, this is commonly used in extragalactic studies to classify galaxies based on if they're star forming or AGN, or this other class of galaxies called liners. And it turns out a lot of the pointings we have towards this tilted disk structure align with this liner class of galaxies. So this makes the Inner Milky Way our closest example of such a liner system, and really lets us study what liners are in more detail. So the overall outline I'll be covering is, I'll start off with the discovery of our nearest liner, which is what I just did here. I'll now actually introduce you a little bit more into what liners are, with a brief history on how they were first seen and why they're interesting, and also discuss some possible sources of ionization. I'll then move back into the Inner Milky Way with, again, a brief history on how we started to understand the extreme kinematics involved and some models of gas dynamics. And then I'll end with some of our newest results on ionized gas with WHAM, which involves adding the Milky Way to this BBT diagram and comparing it with other galaxies. a new modified model associated with this tilted disk structure, and also how it all relates with the Fermi bubbles in the center of the galaxy. Okay, so a brief intro on LINERs. It stands for Low Ionization Nuclear Emission Regions. It's really just a descriptive name kind of describing what you see. So gas is in a low ionization state. It's often seen in the nucleus of a galaxy, but sometimes also farther away, which is why the nuclear term here is in parentheses. And it's emitting in optical light. So a brief history on how they were first initially discovered. If we go all the way back to 1909, when FATH first discovered optical emission from ionized gas in an extragalactic source, didn't even know it was another galaxy at the time until later on when Hubble came around and realized that these spiral nebulae are actually not within our galaxy. That kicked off a lot of surveys of galaxies to try and classify large samples of them using bright optical emission. So a lot of these were led by the Mount Wilson Observatory and also Lick Observatory. So Hermison and Mayall led some of these initial surveys where they found many galaxies to have ionized gas in their inner regions. They started to build more puzzles as time went on. So in 1960, Guido Munch discovered ionized gas in the inner region of M31 and Andromeda. But here, there wasn't any star formation where there was ionized gas. And at the time, there wasn't a clear explanation for what could be doing the ionization for this gas. Later on, more surveys of galaxies, especially led by Margaret Burbidge and Geoffrey Burbidge, started to find that there was a high nitrogen 2 to H alpha in the inner regions of a lot of these galaxies, especially the ones where there wasn't star formation. And that was a big puzzle at the time and was really poorly understood on how you could have such a high nitrogen 2 to H alpha ratio. It could be from really high temperatures, high metallicities, lots of different things can go into it. Eventually, 20 years later, really, these classes of galaxies were coined the term LINERs by Tim Heckman. And that was how people started to understand LINERs. And we now think that about a third of all disk galaxies are, in fact, LINERs. And they're very common in elliptical galaxies. So what are some possible ionization sources? So if we go back to this BBT diagram, it was originally a diagnostic made to understand what the dominant source of ionization was, whether that's from actively forming stars, AGN, some mixture of the two in this composite classification. And then LINERs is the mysterious category here because it's not actually a source of ionization, it's just a descriptive name for what is seen. Some possible sources of ionization are, they could actually just still be AGN, but just low luminosity AGN. It could arise from cooling flows of accreting, as matter is accreting onto that black hole from the radiation leaking off of there. Shocks can also explain some of the line ratios seen with LINERs, so those are often believed to be a possible source. And then more recently, what people have been very convinced about are classes of stars called hot low mass evolved stars, or HOLMs. So these are low mass stars that in their late evolutionary stages, either as white dwarfs, planetary nebula, post-AGB stars, or other types of subdwarf O and B stars, they still have, they're very hot, but very low in luminosity. And if you have enough of them, they could potentially get you to the state of LINERs that you see in other galaxies. They're also really frequently seen in elliptical galaxies. So again, where there's really little star formation and just lots of these older stars, and they're somewhat associated with UV upturns in these other galaxies. And within disk galaxies, they tend to be more common in barred galaxies. So in this diagram to the right, the stuff in orange, especially on the histograms, you can see it a little more clearly. The stuff in orange is just from barred galaxies, and blue in non-barred galaxies in SDSS manga. And you can see that the barred galaxies tend to have this like wider distribution, especially across nitrogen 2 to H alpha, that the barred galaxies are more prevalent in LINER space. And that's seen in nearby galaxies as well as in large samples of SDSS galaxies. Okay, so back to the Inner Milky Way. If we go back to a wonderful review article by Oort, he starts to hint at these ideas that the inner galaxy was kind of fueled by expulsive phenomena. So he was really leading this picture that some large explosion had taken place in the center of the galaxy that was causing a lot of chaotic kinematics and motion in the center. So initially, when you make these observations, people started to observe small features in what you observe, especially in H1, as individual arms, clumps, rings, and little like features that were moving independently and separate. So you have these like massive complexes of molecular clouds. This is a hand-drawn image, really, of what they thought could be happening near the center of the galaxy from 1960. It's just a digitized version of that. So you have all these like interesting high-velocity streams, a lot of discrete structures and features. But you can also explain this, it turns out, if you unify everything into the picture of a bar-like motion. So in 1980, Butler Burton and Harvey List started with a circular tilted disk model that brought a lot of these individual features into a single unified structure, and that eventually evolved into this bar-like structure of gas flowing in elliptical streamlines, roughly aligned with our current day knowledge of the bar. But the key is that it is tilted from the rest of the plane of the galaxy. So in this image, this is an H1 image from H14 pi, but we're looking at just these forbidden velocities of gas. So from your standard galactic rotation, you would expect that in the inner galaxy, everything to the left would have positive velocities, radial velocities, while everything to the right would have negative radial velocities. So this map is by doing exactly the opposite, looking at just negative velocities to the left and just positive velocities to the right. And what you see is the structure that looks tilted and somewhat connected across the center of the galaxy. And this is what the tilted disk is. The contours here are from their original model from 1980 of H1 associated with this tilted disk structure. So some downsides of using this old geometric approximation is that it doesn't have any type of radial or azimuthal density variations. So what we can do is turn instead to hydrodynamic simulations to better understand what gas is doing in a bar potential and try and figure out what this tilted structure really is in our galaxy. So this is an animation from Matthias Romani and his collaborators groups in Heidelberg, looking at gas flowing in a static bar potential. And it does a really nice job of understanding the kinematics of gas in the CMZ and gas flowing along the bar in general. So what this is showing is just H1 in both a face-on view and just an edge-on view as well. What you should notice is a lot of the gas gets coalesced into these thin bands that are frequently called dust lanes. So most of the gas is just flowing in radially along these dust lanes as they reach the central molecular zone in the center. And a lot of the rest of the ISM has these large holes and pockets of evacuated gas. So some of the issues with this model, with this simulation, is that the gas layer tends to be too thin compared to what we actually see. It also is, in a sense, too neutral. There's not actually any hydrogen ionizing radiation field in the simulations. There is some ionized gas that arises from shocks, but no photons from hot stars or any of that is involved. So we don't see very much ionized gas compared to what we actually observe. And a key aspect here is that it doesn't explain the tilt. So the gas in the inner galaxy does appear to be tilted, especially in the inner, like 1.5 kiloparsecs, and the stuff in the simulation does not support or like see that tilt, and it's still not very well understood what is actually causing the tilt. But it is an important observational feature and pretty key to our results in optical light because it's the only way we can actually see through the dust. So because of this, we understand the kinematics are complex. It matches qualitatively to the geometrical approximation. So we do just go back to this geometric model to better understand the bigger picture of what we're seeing. And so to turn to what we're seeing, we're using WHAM, the Wisconsin H-alpha mapper, to detect our ionized gas. If you don't know WHAM, it is the most sensitive telescope in the world of its kind. It's funded by the NSF. It's currently in Chile at CTIO, and it observes lots of optical emission lines in a way that's somewhat similar to like a single dish radio telescope, but for optical light. But it has a 1 degree beam. So it takes all the light you see within a 1-degree patch of the sky and converts it into a single, very deep spectrum for H alpha, H beta, nitrogen 2, sulfur 2, oxygen 3, and a few other lines as well. And so what this animation is showing is just H alpha from the full sky that's been done as part of the full sky survey at a few different velocities and rotating through different longitudes in the sky. And you can see mostly at the moment just local ISM, large H2 region, supernova remnants. But the power here is that we have actual spectra for each of these points. And if we do some targeted, deeper observations, we can actually see some of the high velocity features associated with the galaxy, especially in the inner galaxy. If you're interested in using this data, the full sky survey is public. You can also access it with a Python package, WHAM-Py. And so here's a quick little video kind of highlighting the discovery of this tilted disk. So this is like a rendition of that model as where it would lie towards the center of our galaxy. It has this flaring structure for the ionized gas, and that allows it to peek through in the bottom through that low extinction window when we look at it from the Earth's position. So you can see a little bit more that the ionized gas structure we model is flared. It gets about twice as thick on the outer regions than in the center. And it is pretty roughly aligned with the bar, though not perfect. So we go back to what we're actually seeing. So just through this low extinction window is where we have our main H alpha and other line detections. And that actually aligns pretty well with what the model predicts as well, which I'll show in the next slide. But when we start to look at the line ratios across the structure, we also notice a nice trend as when we go from as close to the center of the galaxy as possible, we see the spectra as more like star formation. And as you go farther and farther out in radius from the center, the line ratios get higher and higher, and we get towards this liner regime of line ratios. And that's much different from those green points at the end, which are from the Scutum cloud, which is about like 4 kiloparsecs away from the center of our galaxy. And we think this is more typical of what most of the diffuse ionized gas or warm ionized medium in our galaxy would look like on this diagram. So the structure is really distinct from the rest of the galaxy. It's somewhat more extreme in a sense, but it's also liner-like, which will help use the Milky Way as a way to better understand what liners are in the role of evolution of galaxies. And so with this model that we have of this flaring disk of gas, what this image to the left is showing is just what a synthetic image of H alpha would look like when you pass it through 3D dust extinction estimates. So we use Baystar, so the 3D dust extinction maps from Greg Green and Doug Finkbeiner's group at Harvard, and pass in our model through that extinction map, and this is what we would expect to see. And what you should really focus on is down here in this negative velocities towards Bada's window. This is pretty much exactly where we do detect our H alpha gas from WHAM. We don't yet see any of this, but it is also much fainter, and we just haven't had the time to do the observations there. But the model, even though it's very simple, pretty much predicts that we'll see H alpha only where we do observe it. Everywhere else it will be blocked by extinction. The nice thing about having this model is that we can start to estimate things like what we think the total ionized gas mass would be associated with the structure and in the center of our galaxy. And we find that we think that the ionized gas mass is probably higher than the neutral gas when we're just considering atomic hydrogen. So a factor of about 2 to 3 higher in terms of ionized gas than neutral gas. It also has a pretty large flaring scale height as you get farther out in radius. So it's about twice as thick on the outside, on the outer edges of it than the inner parts. And generally we think of it as a ring as opposed to a full disk. Some of the other things that this model lets us do is start to estimate what kind of ionizing radiation field would be necessary to power this kind of structure and support it. So this is, again, just a rendition of what this model would look like, where the hatch stuff is from the ionized gas and the neutral gas layer doesn't flare and is just the solid colors. And so if we estimate what kind of ionizing flux as a plane parallel flux would be required to do the ionization for the structure, assuming the model, it would take about 10 times as much of the ionizing flux that is required in the solar neighborhood, which isn't too much and not that unrealistic, seeing that as we go to the center of our galaxy, our stellar density is increasing. We especially think we'd see more of these older, hot, low mass evolved stars. So that could also support the idea of this structure being liner-like. Alternatively, we could also find the ionizing photons if we just allow about like 5 to 10% of the radiation from the central molecular zone to leak out just from the nuclear star cluster of O and B stars there. So that is also another way you could do this, and it's not terribly unrealistic, especially if we go back to the hydrodynamic simulations where there are lots of like pathways that the radiation could escape. A lot of the 3D photoionization modeling that's been done for warm ionized gas typically looks at the vertical distribution of gas, and photons from these dense regions are able to escape because of turbulence and cosmic ray streaming. You could imagine the same kind of thing being able to propagate through radially, but it does need some more modeling to be able to say how that could actually affect the ionization in the center of the galaxy. And so lastly, we can kind of start to relate this to the Fermi bubbles and see how it all ties into a big picture. So this image should be somewhat familiar. I know Jay and Naomi first put together this view of the H1 as you're approaching galactic center along the tangent points, where you see that the H1 gas layer is thin and then starts to get pretty thick and flare outside the boundaries of the Fermi bubble. But one of the nice things about this map, for me at least, is that you can actually see the neutral tilted disk or some signatures of it here. So you can see there's this tilted looking gas here, and it's a little bit offset here. So here I'm just adding on what the model predicts for that tilted disk structure to look like, and it fits pretty nicely that you can see it here. So because this structure, the tilted disk and the bar in general, have pretty extreme kinematics compared to the rest of the galaxy, it's really important to understand how all of this ties together into the Fermi bubbles and how the Fermi bubbles can interplay with the disk. So it seems like what's happening near the center of our galaxy is a lot of gas is flowing into the center along the bar and then can be ejected out in this large scale nuclear outflow. And trying to understand how the conditions of the gas change as you go from one to the other is really important. One other thing to look for here is that some of this flaring could be explained by just the bar itself. So this is again that H1 map towards the tangent points. On the left here is an animation from a simulation, the same simulations as before, from Matthias Armani. So this is gas flowing in a bar potential with some feedback from stars. There's no nuclear outflow in the simulation, and the vertical extent is pretty much well explained by just hydrostatic equilibrium. And while not a perfect match, you do see that there is some of this flaring effect as you approach the center of the galaxy, if you ignore the center as an artifact. But in general, you can see the red dots here are the footprint of the Fermi bubbles. It still kind of nicely fits into what the gas layer is doing. Again, it's not so in reality the gas is staying quite thin for longer than it is in the simulations, but the effect of the gas layer getting more compressed towards the center of the galaxy could also just arise from the bar. So it's really important to try and understand how much the Fermi bubbles are contributing towards this compression of the gas layer versus how much the bars are doing. And it looks like there's a combination of the two happening. One important question here to think about is whether the nuclear outflow and the Fermi bubbles are then providing a source of pressure to compress the ISM further, or if it's just the bar is already compressing the ISM and sort of evacuating the space, and that's allowing a nuclear outflow to pretty quickly fill that evacuated space in the ISM. So understanding like which came first, what's causing the other is sort of a question that we can start to look at by better understanding how stuff in the bar is tied to the Fermi bubbles. And so what we've done recently is we've turned to some previously detected UV absorption from quasars that have lines of sight passing through the Fermi bubbles. So in 2015, Andrew Fox and some collaborators looked at the quasar PDS 456. It's relatively low in latitude, about 10 degrees, but still passes through the Fermi bubble near the edge. And they're able to see absorption at high negative and high positive velocities that are pretty consistent with what you would expect for a biconical outflow from galactic center. And this was one of the first times that a velocity measurement was made for associated with the Fermi bubble footprint as a 2D morphological structure. So this is some of the really convincing evidence that the Fermi bubbles were in fact an outflow from the center of our galaxy. What we've been able to do is look in the same direction with WHAM and target deep observations of optical emission in H alpha and nitrogen 2. And we found at the same high negative velocity where you have the UV absorption, which is where this line is, we also see H alpha emission. Here just zoomed in to that emission, and it's almost an exact correspondence to where the H alpha emission and the UV absorption were. And what this allows us to do is now we can use a combination of both of these to infer some properties of the ISM and make some in situ measurements. Because the emission from optical emission as a recombination line depends on the ionized gas density squared, and the absorption provides a measure of the ionized gas column density, and in a sense, just a measure of the ionized gas density. So by combining the two, without assuming a model, we can infer what the ionized gas density and its emitting path length and some more properties of the gas actually is. So what we've done, so here is some of the absorption line spectra from HST. By using all of the silicon absorption that's seen, silicon 2, 3, and 4, we can try and estimate what a total ionized hydrogen column density is, assuming some metallicity as well. And then use that in combination with the H alpha emission, which you can get an emission measure out of. We could apply extinction corrections using an approximate distance towards galactic center and towards the structure. And what we get are these in situ estimates of the ionized gas density, the path length is coming from, temperature, and also pressure. So what we're seeing is gas that is quite dense, especially for gas that's about a kiloparsec off the plane of the galaxy. It also seems like it's coming from a very compressed zone, so coming from sub-parsec scales in terms of the path length that it's being emitted from. There is a large uncertainty with the temperature, but it seems to be relatively warm and consistent with what we see throughout the galaxy. But because of the high densities, the pressure of the gas is also very high. So it's about a factor of 100 higher than what you'd expect for gas at this height in the solar neighborhood. It is quite high, but some also consistent with another estimate that's been made towards the Fermi bubbles from a different sight line, LS 4825, that looks just below galactic center. There a similar high pressure was also estimated, I think a little bit higher than this as well. But this pressure is also consistent with what models would expect. So the Miller and Bregman Fermi bubble and hot halo models both would predict comparable, but still slightly lower pressures associated with the gas at this location. So the other key result of what we can do with this new H alpha detection is that, unlike when looking for UV absorption or even looking for H1 outflows, we're not limited to either background sources or like clumpy, sparsely distributed clouds of gas. We can actually start to try and make a continuous map of what the ionized gas in the shell of the Fermi bubble looks like. And some of our initial attempts to do so show some preliminary observations here of where we're detecting H alpha in relation to where the PDS 456 is. And we start to see that we see this high velocity emission that seems to be distributed across a relatively large area of the sky. And it's a somewhat continuous map of this H alpha emission. So it looks like what we're seeing is the shell of the Fermi bubble where the gas seems to be under high pressure and compressed, and coming from like a thin zone within the shell of the bubble itself. And it seems like it's pretty well extended. And what we can do in the future is actually extend this map to try and map out the entire shell of the Fermi bubble, look for boundaries, see where it actually would cut off and compare that with model estimates, and also search for velocity trends and gradients. So we can actually measure how the velocity is changing as both a function of longitude and latitude to better understand the 3D picture of what this outflow looks like. So some future prospects and some conclusions. One other thing that we're seeing towards the Fermi bubbles is a low nitrogen 2 to H alpha. So unlike in the tilted disk where we have this liner-like line ratios with high nitrogen 2 to H alpha, once we get the gas actually gets ejected out, it seems like the line ratios are much lower and actually somewhat consistent with a decreased metallicity of about 30%, which are what some other estimates for halo gas or Fermi bubble gas are showing. We've made these in situ measurements for the first time of ionized gas associated with the Fermi bubble shell that seem to be under a large pressure, which is generally consistent with predictions from either a hot halo or Fermi bubble models, but still suggestive of a further overpressured zone that we're seeing. And tying this back in with the tilted disk in the bar. So within the bar, there's a tilted disk structure in the inner galaxy that's substantially ionized. We think it's at least 50% ionized in terms of the atomic hydrogen. Here, the optical emission line ratios are more extreme and consistent with liners commonly seen in other galaxies. And this is really important because it opens up an entirely new avenue on a way to constrain the mysterious sources of ionization and heating associated with liners, but we can do it from within the Milky Way, where it can actually start to resolve out individual sources and have more detailed models to understand the 3D distribution. So in the future, what we hope to do is sort of combine this all together to have a unifying picture of what's happening with gas flowing in the bar, how it outflows in the Fermi bubbles, and how they both relate to one another, and connecting that disk halo interface as close to the center of our galaxy as possible. And one of the ways I'll plan to do that is by using UV absorption spectra from HST and more WHAM observations to do so. And so I'll stop there and take some questions. And I do have some other bonus slides I can also show if anyone would like.
I guess I had one question. So how does the tilted disk that you're looking at in the bar, how does that relate to the dust lanes that Matteo Sormani predicted for gas flowing into the galactic center? Like, is it associated with that, or is it located inside the dust lanes? Do you have a understanding of where this would be located relative to those?
Yeah, so in the simulations, so in the observations, the dust lanes also do have a slight tilt associated with them compared with the rest of the galaxy. Let's see if I can find this. So in the simulations, the dust lanes are not tilted. In the real observations that we see, the structure associated with the dust lanes in H1 and CO does have a slight tilt. But the tilted gas that we're seeing is somewhat aligned like in this region. So it's not quite associated with the dense gas that's flowing in the dust lanes itself, but better fits the stuff in the diffuse areas around here. So specifically what we're detecting is gas that's kind of flowing back outwards after it tries to reach the CMZ and quite doesn't make it. So this gas that's kind of flowing out in the simulations are more consistent to the gas that we're seeing in the tilted disk. So in reality, like what we're observing is probably this section of the gas where there seems to be more of a tilt. but it's not really well matched in the simulations. The extent of the tilted disk that we're seeing also isn't quite as large as the full bar or dust lanes. It kind of is probably about half of the radial extent.
This is Jay Lockman. I've got a couple questions. What's your understanding of the low metallicity in the Fermi bubble?
Honestly, I don't think we have a very good picture of this here. So a lot of the evidence for the metallicity in the Fermi bubbles are less estimates and more just like somewhat lower limit constraints. So the 30% comes from the one I've seen is from a different sight line at a higher latitude, where some photoionization modeling with cloudy was done that constrained the metallicity to be at least 30%. It was a lower limit, but they also estimated that it was probably pretty close to 30%. I wouldn't say that like our result has a constraint on the metallicity, but instead, what I would say is our nitrogen 2 H alpha is low, and with the temperatures that we estimate using the line widths, it's too low. But if instead the metallicity were lower, around 30%, it's a better match to what the predicted line ratio would be at our given temperatures. We're estimating our temperatures just by using all of the line widths of both the UV and the optical lines that we have, and sort of combining those to decompose it into a thermal and non-thermal line width.
And with regard to that other image that you just showed a moment ago, the new H alpha measurements where you see high velocity, yeah, I guess, yeah, that one right there where you have, it's blinking in and out. But you're detecting high velocity as in minus 100 or minus 200 H alpha emission all the way down into the galactic plane?
Yeah, so this is about like minus 250-ish kilometers per second. Not all these detections are that great, so this is that same kind of map, just kind of zoomed in to where we did it. So the open circles are all the places we have observations made. Anything that's red is at least a 1 sigma detection, so pretty weak. And the solid blue lines where we have 2 sigma detections. And it does seem like we have some of it pretty low in the galactic plane at these high velocities, which is definitely pretty surprising. So as you get closer to the plane here, it gets definitely more confusing because this could start to be associated with the bar. So that's kind of more of why it'll be nice to kind of model all of this together with the bar and Fermi bubble. So it's not really clear to me what this gas is down here, but up here it's more consistent with Fermi bubbles predictions. And it'll be nice once we can expand this further to see how things are changing. Like right now, I don't know if we see the edge of the Fermi bubble or not, but in the future we might be able to test that by going farther out.
So the emission measure must be ferocious in those low latitude sight lines to punch through all the extinction.
Yeah, it seems like it. So this panel on the right is essentially a map of the extinction, where let's see the colors here. So the white is, so this is by passing just like a constant surface brightness H alpha slab at a fixed distance through the 3D dust maps. Where white means we don't see any of the emission anymore. Red means we see it. So there's some patches here where there's low extinction, even though we're close to the plane, that we might be able to see pretty far into the center of the galaxy, even without it being too bright. But other places where we do see it, it must be pretty bright in order for us to see it probably, or it is closer.
I guess I had one more question. How long were your integration times for these H alpha, I guess, pointings in order to get that type of sensitivity?
Yeah, so this map is just 60-second observations, I think. It might even be 30-second observations. No. So this is 2-minute pointings for each of these points, which is very little. So we have pretty bad signal here, which is why our detections are pretty faint. For the one deep pointing that we made towards PDS 456, it's closer to 30 or 40 minutes for H alpha, and another 30 or 40 minutes for nitrogen 2 separately. So that gives us about like 10 times better sensitivity. We do have a few other directions in the southern Fermi bubbles that we've also observed with some deep observations where there's UV absorption. So that's something we're working on now to see how other parts and other sight lines could compare.
Do any of these pointings overlap with the H1 clouds in the Fermi bubble? Do the velocities that you measure, are those consistent with what you see for the H1 clouds?
The velocities in general seem to be somewhat consistent, but so for this sight line in particular, PDS 456, there were deep GBT H1 observations made, and they were only able to get an upper limit. So in this direction, it seems like there's not very much, if any, neutral gas, and it's mostly ionized gas. But the velocity that we're seeing seem to be roughly consistent with what some of the observed H1 outflowing clouds are. Once we have more data, we'll be able to better kind of test the predictions there from both simulations and what's observed to look for those velocity gradients.
All right, any last questions for DK? All right, well, thank you all for joining us this week. Next week we will have next week we will have an NGBLA talk, and we will meet up again this time at 12:15 next Thursday. All right, see you all then.
Thanks.
Thanks, DK.